Hello, everyone, and welcome to RIEGL's webinar series. I'm Michael Sitar, and today's webinar is Caught in the Crossfire, Up Close and Personal with RIEGL's VQ-1560 Wide Area LiDAR Mapping Sensor. Today, we're going to cover a number of different topics, but our primary focus is on LiDAR scan patterns. We'll take a look at the impact on point distribution and target coverage, a brief discussion on target characteristics and application examples, and then more closely at the RIEGL scan patterns themselves. Following that, we'll discuss sensors and scan pattern options as they relate to wide area mapping, and then a closer look at scan pattern versus point density. And finally, a close-up of what is, in fact, the crossfire pattern, the geometry, the data streams, what is the impact on the nominal point spacing, how does the crossfire pattern improve our target coverage, and we'll be demonstrating that with some model simulations, followed by a city example. And then to wrap things up, a few benefits and best practices. In a perfect LiDAR world, end users should rarely concern themselves with scan patterns. All 3D objects should have complete and total coverage. However, given our complex world, platform limitations, and many application needs, pattern does play a role in the outcome of collection and data results. The chosen scan pattern is really just a mechanism to achieve the desired model coverage and sampling distribution. Therefore, from a design perspective, point distribution and target coverage can be optimized in the following ways. With respect to point distribution, it can be optimized by the choice of sensor scanning mechanisms, whether this be rotating polygons, rotating prisms, galvanometers. The choice of detector, is it a single versus segment detector? Is it an array? How many beams are in the optical design or the system design? And as far as target coverage, it can be optimized by the sensor scan geometry, the sensor orientation, pitch, hole, and heading, the flight plan configuration itself. What is the percentage of side lap? What are the flight line orientation relative to the target model? And finally, the solution configuration. Are we talking a single sensor, multiple sensors? In the past, sensor scanning system design paid less attention to scan geometry and application suitability than they did to simple range performance and point density. In addition to expected incremental improvements, industry trends and expectations are now demanding sensors that are optimized for productivity, point distribution, and coverage as they relate to the applications themselves. Manufacturers are developing scan configurations to provide the best possible target coverages. In doing so, it's helpful to review the target coverage as a function of both target morphology and application detection requirements. Generally speaking, target morphology can be broken down into the following characteristics. Hard targets. These are targets that intercept the entire laser footprint. These can include examples such as roadways, open ground, and generally only one laser return is recorded. Soft targets. These are targets that interpret only a portion of the laser footprint. Samples of this include power lines, transmission towers. Generally, multiple returns are collected from an outgoing emission. Complex targets. These are targets that intercept both partial and full laser footprints, and generally also have multiple returns. Examples of this include forest stands, buildings and their building edges. And finally, occluded targets, targets not visible to the laser transmission path and or the receiver field of view. Examples of these hard, soft, complex targets include ground surface models for floodplain mapping. Soft targets are power line catenary models, and forest structural analysis, asset inventory, or even urban mapping when it comes to complex targets. RIEGL's objective is to provide LiDAR sensors that have optimized scan geometry and target coverage for a variety of popular market applications and are scalable in configuration for existing and future applications. Some of the scan patterns that are offered by RIEGL products include a planar scan pattern. This provides full scene visibility and global coverage when co-mounted with additional planar scanners. A conical scan pattern is utilized by our bathymetric sensors. It's a fixed off-nadir field of view, which allows water penetration and the reduction of specular reflection from water surfaces. This pattern is also used in our UAS sensor portfolio, primarily the MiniVux downlook. It increases vertical density and provides a fore-aft coverage on a single flight pass, particularly as it relates to corridor mapping. And for the discussion today, we'll be focusing more on the matrix scan pattern, available in a number of different topographic sensors available from RIEGL. The matrix scan pattern is in essence parallel scan lines that ensure semi-uniform point distribution throughout the entire field of view. And finally, the CROSSFIRE scan pattern. This is a 2x matrix pattern. It provides a multi-perspective scan geometry and enhances the vegetation penetration and provides increased vertical density and occlusion avoidance. When it comes to wide area mapping, there are a number of linear LiDAR sensors to choose from, all with their own unique scan configurations and each with their own inherent advantages and disadvantages. The following scan geometries are presently available as single sensor solutions. The first is the matrix scan, as I mentioned in the previous slide, with our VQ-1560 Mark II. This is a single laser solution with a flush mount design, and the laser is directed through the optical path onto a rotating polygon with a fixed field of view of 60 degrees. In the pattern you see below you. The CROSSFIRE pattern is a dual laser configuration, again in a single sensor chassis. Unlike the VQ-1560, this is a drop-in system design with a 58-degree field of view emanating from a rotating polygon. Other options on the market for wide area include circular scan patterns, single laser sensor configurations, again, a drop-in system design, utilizing a Risley prism as the scanning mechanism. Users have the option to choose from 20 to 40 degrees field of view. And finally, a sawtooth scan pattern. Again, a single sensor chassis configuration, in this case, a flush mount system design similar to the VQ-1560, but with a user selectable field of view that ranges from 10 to 60 degrees. In this case, using a galvanometric scanner to propagate a sawtooth pattern on the ground. LiDAR projects are generally specified for required mean point density. Scan pattern can have a significant impact on the distribution of that density across the scan width. In the following slides, we will review model density distribution as a function of maximum sensor parameters for the various wide area mapping systems previously identified. As a baseline, all sensors were modeled and altitude adjusted to maintain the same swath width of 728 meters. Similarly, a common velocity of 100 knots was assumed. With these constraints, maximum effective pulse repetition rates and maximum scan rates, as described in online literature, were used. Distances of all consecutive points along track and across track were measured as they intersect the model ground surface to determine for each sensor the point density model, as per the equation below. The matrix scan in this case that we will look at will utilize, as I mentioned earlier, a 60-degree field of view. For the emitted pulse repetition rate, we'll be using the effective rate for our density calculation, which is a 1.3 megahertz ground sample rate based on the polygon scanner that's used, and with a maximum scan speed of 300 lines per second. And in this configuration, with these parameters, it equals the XY point distribution is close to being equal. With the CROSSFIRE, we'll be utilizing the 4 megahertz sensor, the 1560, and in this case has a maximum scan speed of up to 600 lines per second. Again, to maintain the equivalent swath width, the slightly smaller field of view, we'll be flying a little bit higher at 650 meters. Again, the nominal point spacing is planned with X equal to Y. The third scanning scenario we'll be reviewing will be the circular scan pattern. In this case, we'll be utilizing the maximum field of view available with 40 degrees. And in this case, also the effective PRR is in fact the same as the advertised PRR. This sensor has a maximum scan speed of 300 lines per second, and when modeled at 1,000 meters, AGL again has a nominal point spacing of x equal to y. And finally, a sawtooth scan pattern. We will utilize a 40-degree field of view. Again, the effective ground sample rate is equivalent to the advertised emission rate of 2 megahertz. This sensor utilizes a maximum scan velocity of 200 lines per second. In this case, based on the advertised altitude and the velocity at the scan angle, the nominal point spacing isn't quite equal to x equal to y. The following charts illustrate the relative point density distribution of a single pass of the various scan patterns employed in the linear LiDAR sensors available today. Each chart is divided into scan quadrants of 25%. The perfect scenario is a point density chart that has equivalent point density at nadir as it does at the scan ends, or a straight horizontal line. Due to the angular differences that propagate from nadir, this is inherently not possible. But the choice of scanning mechanism does have a significant impact on the overall distribution of the available points and resultant density on the ground. However, know that driving algorithms and PRR attenuation can have a significant impact on the density distribution across the scan. These factors are not considered in these models with linear velocities and fixed PRR assumed across the full field of view. For the matrix pattern, the minimum and mean point density values are very similar to each other, with the points within the central portion of the scan actually above the mean value. In this case, the mean value is often a conservative estimate of the actual density within the primary portion of the scan. The minimum point density of the matrix pattern is also very similar, if slightly lower, to that of the circular scanner, despite the 30% increase in field of view. With the circular pattern, the delta between the minimum and mean point density values is much larger and is in fact inversely associated with the central scan area. In other words, the mean value does not adequately reflect a minimum point density requirement in the central portion of the scan where it matters the most. The central scan is underrepresented and is far less than the mean density. In this case, a full 75% of the scan FOV is less than the mean value, and a further 50% is less than the matrix pattern maximum density in the scan center, even when the advertised PRR is equal to the effective PRR. An even higher PRR or oversampling or much higher mean density values required to make up for the density deficiency in the central scan areas compared to the matrix scan. This chart illustrates point density when flying with an adjacent flight line with 20% side lap. In this case, the minimum point density is now above that of the circular scan. Although point density is now higher at the edges of the swath compared to the single swath coverage on the previous slide, the matrix pattern is able to maintain the required overall minimum point density due to the overlap of the neighboring scan line. Overlapping scan lines are necessary anyways when doing wide area mapping projects, and so can be considered as part of the overall density calculation. Also, it should be considered that the already extremely high point density at the outer edge of the swath for circular scan patterns will be doubled again due to the overlap, without necessarily gaining any additional information. For example, 10 square meter footprints on a square meter object does not give you 10 times more resolution than a single square meter footprint on the same square meter object. For that to be the case, a reduction in beam footprint is required, whether it is by flying lower or using a smaller beam divergence value. In this case, the addition of the second matrix channel in the VQ-1560 creates the CROSSFIRE scan pattern and provides a similar yet randomized point distribution to the VQ-780 matrix pattern, but with double the density capability. With both sensors at maximum PRR, that is 2.66 megahertz versus 2 megahertz, for the equivalent swath width, the CROSSFIRE sensor is able to provide almost 2 times the minimum density capability in the central portion of the scan at a full 60 degrees, compared to the 40-degree field of view of the circular scanner. For the matrix pattern, again, the minimum and mean point density values are very similar to each other, with the points within the central portion of the scan actually above the mean value. In fact, almost 50% of the points in quadrants 1 and 2 are above the mean density value. With the sawtooth pattern, similar to the circular scanner, the mean point density is much larger than the matrix pattern, and point density increases outwards. However, the larger mean point density, therefore, is a necessary requirement to achieve a similar minimum point density in the central scan portion. In this case, it is still less than the matrix pattern at nadir, i.e. 35 points per meter squared versus 40 points per squared based on this model analysis. Similar to the circular scanner, a full 50% of the scan is less than the mean value, and this is entirely within the central usable portion of the scan. Again, the central scan is underrepresented and is far less than the mean density. In this case, an even higher PRR or LESO FOV is required to ensure the minimum density deficiency in the central scan area is overcome. Finally, the addition of the second matrix channel in the 1560 provides, again, a similar point distribution to the VQ-780, but with the double density capability. With both sensors at maximum PRR, 2.6 megahertz versus 2 megahertz for the equivalent swath width, the CROSSFIRE pattern is able to provide almost 2 times the minimum density capability in the central portion of the scan at a full 60 degrees compared to the 40-degree nominal field of view of the sawtooth scanner. It's also important to note that the lower altitude or relative flying altitude for the equivalent swath width also translates to a smaller beam footprint on the ground, thus increasing overall target resolution capability by roughly 25%. So what exactly is the CROSSFIRE scan pattern? Why is it so effective in so many applications? The CROSSFIRE pattern is the result of a 2-channel laser optical design with a beam path that is directed toward opposing facets of a single rotating mirror. This produces 2 interleaved matrix scan patterns of consistent point distribution that, when combined, appear as a randomized yet homogeneous point cloud across the entire field of view of 58 degrees. The beam channels are first pitched fore and aft. At nadir, the pitch angles converge to 0 degrees to ensure maximum avoidance of data occlusions. And this nadir look angles is essential for getting coverage into narrow street canyons and small inner courtyards. At the scan ends, the fore-aft pitch angles diverge to ±8 degrees, significantly improving the sensor's ability to increase point density on vertical surfaces. The beams are also counter-rotated. They are yawed in opposing directions at ±14 degrees. This provides more complete coverage of building facades and vertical surfaces that would otherwise be obscured as the aircraft passes over the target. It optimally interleaves the double matrix pattern. This slide shows the 2 independent data channels and resulting swath coverages created by the CROSSFIRE pattern. When combined, a double density overlay becomes apparent with exceptional co-registration accuracy. So how do the points of the 2 channels behave? Let's look more closely at the individual channels. In this first image, what you see is a single channel that's colored with the intensity value. This is the same area without the intensity value. And now we're starting to see the points themselves more specifically. We'll zoom in to channel 1 over here on the right. You can see the points there. And zoom in further still, and you can see that they're regularly spaced points even at the scan ends. On the right, this is a zoom in of channel 2. Again, regularly spaced points, but in this case, you can see that the angle is slightly canted relative to the previous image. And when we overlay the 2, channel 1 and 2 combined, on the right is the single channel 2, and with the 2 combined on the left, and you can see now we really have a homogeneous point pattern. And this is at the edge of the scan. So the result is there is no perceptible pattern in the data. The points appear to be completely randomized. It gives the impression of a homogeneous point distribution. There are no better or worse areas to even consider, even at the scan edges. To better understand the impact of sensor parameters on the overall point distribution and density of the various RIEGL sensors, RIPARAMETER is available to do this analysis. Graphic simulations are included to help visualize and optimize the point pattern on the ground. The software provides assistance with determining optimum scan parameters. This is particularly important for setting appropriate PIR and or laser power values when it comes to detection probability of small soft targets that we described earlier. It is always best to plan with a safety margin to account for poorly reflecting targets. At the same time, eye safety must be considered. Wires are extremely difficult to detect as the reflected amplitude decreases proportionally to the third power of the laser measurement range. So in some cases, it may make more sense to reduce flying altitude rather than simply increasing laser power. In order to have a better understanding of the impact of the CROSSFIRE scan pattern on the sampling of real objects, we've derived some simulated point clouds. We've derived them by artificially mounting the sensor on a platform moving at constant speed and orientation over each of two objects. By generating measuring vectors according to known parameters, by intersecting those measurement vectors within the objects, and by simulating 3 flight passes, one at nadir and one on either side with 50% side lap. The two objects are a small house and a building with a flat roof and an inner court. Objects have been considerably oversimplified to illustrate the convergence or coverage of these concepts. We start with the simple house positioned directly below a flight strip and with one wall strictly parallel to the flight path. Channels 1 and 2 are shown as independent collections, although flowing simultaneously. You can observe the opposing scan orientations relative to the building. Since the sensor is flowing directly over the building, the nadir view does not reveal building walls at this point. However, as the targets move outward from the nadir flying position, the counter-rotated beams will start to map the building facades, which I'll show you in this next slide. And here, the combined channel interaction on the model to the left. And now the model to the right includes the flight passes that are 50% offset to the nadir pass. And you can observe that all 4 sides of the building are now visibly mapped. Now to the building with the inner courtyard. Similar to the first building model, channels 1 and 2 are shown as independent collections flowing simultaneously. Again, notice the opposing scan orientations to the building, although this time, due to the nadir look angle, the inner courtyard floor has been successfully mapped. Again, this slide shows the combined channel interaction on the model to the left. The model to the right now includes flight passes that are 50% offset to the nadir pass. All 4 sides of the building are now visibly mapped, as well as the interior walls of the courtyard. So this brings me to a poll. How important is scan pattern? Collecting the responses. And I'm closing the poll. And it looks like 92% feel that the scan pattern is critically important. So that's great. Well, let's now look at the demonstration of our models in a real-world environment. The following 4 slides provides a practical example of the CROSSFIRE pattern in an urban setting. When we review the model with just a single pass and a single channel, it's clear that there are missing exterior and interior facades, particularly when the facades are parallel to the scan direction. We are also missing facades perpendicular to the scan direction due to the close proximity to nadir. However, courtyard floors and narrow passages are accessible from the nadir look angle. With the addition of the second channel, facades now appear on exterior walls that were parallel to the scan direction of channel 1. And now as we add channel 1 of the neighboring flight line offset by 50% to the first flight line, we can see that the inner courtyard facades and some exterior facades that were close to nadir of pass 1 are now visible with pass 2 edge scans. And finally, with the addition of channel 2 of pass 2, we are left now with a wholly complete urban model of all interior and exterior facades, inner courtyards, and narrow street passages in the urban canyons. Some interior tight corners are missing toward the bottom of the courtyards, but all narrow streets and building facades are covered. In this case, no perpendicular flight regimes are required. Unlike any other airborne system on the market today, the unique geometry of the CROSSFIRE scan pattern to simultaneously provide both nadir, off-nadir, and counter-rotated look angles is essential to providing complete structure coverages, especially in complex environments such as forests, urban centers, and infrastructure projects. To reiterate, the inclusion of a nadir or 0-degree look angle is essential to penetrating the building canyons in inner courtyards or forest canopies. The CROSSFIRE scan geometry of the VQ-1560 maintains both the nadir and off-nadir look angles for the most effective coverage and canopy penetration possible, while ensuring the best possible point distribution throughout the entire field of view. And this is a 3D representation of the photographs or the image renderings I just showed you, illustrating the complete coverage of all building facades in the inner courtyards. Again, there are no perpendicular flight passes collected. These are simply 50% offset flight lines. So what are the benefits of the CROSSFIRE scan pattern? Well, it provides a homogeneous point distribution across the entire scan width, which we discussed earlier. It has excellent vertical density for urban, corridor, and forestry applications, specifically due to its pitched fore-aft scan geometry. It has excellent vertical surface coverage with counter-rotated scanning geometry. It has fewer collisions in urban canyons and forested environments with its 0-degree pass-through at nadir. The simultaneous double pass over target areas provide enhanced canopy penetration, ground detection, and density increase. And finally, it has exceptional calibration stability, which is critical for the repeat and long corridor flights. Some best practices associated with flying the RIEGL 1560 with the CROSSFIRE scan pattern is by flying 55% side lap, it allows planning for half density per flight line and therefore higher altitudes to maintain productivity, whilst providing optimum coverage of complex targets and environments. This is becoming common practice for forestry and urban mapping applications for those that utilize the 1560. For those that are altitude restricted or prefer single swath coverages with lesser side lap, the CROSSFIRE pattern still enables fantastic results compared to single sensor scan patterns. Unlike other scan patterns, project planning for mean point density with the matrix or CROSSFIRE patterns translates to higher point density in the interior of the scan, exactly where it matters the most. And finally, fully gyrostabilized solutions eliminate within channel scanline phasing in the flight direction. This is particularly important as lines per second are increased to adequately distribute the higher density points. Density without distribution does not translate to improved resolution. This is the best practice for all sensors, regardless of their scan geometry. And finally, you can run, but you can't hide. The VQ-1560 II will map you. Thank you. So that's the presentation for today. I will hang around for some questions. If anyone has any questions, please let me know. So the first question is, on the first slides, it shows that the field of view of the 780 and the 1560 Mark II is fixed. Does this mean the field of view cannot be adjusted smaller to increase point density for corridors? That is correct. So to be able to provide that homogeneous point pattern, that matrix pattern, these are fixed field of view scanners. And so the density at the middle is consistent with the density at the end. To increase point density further, what we would recommend is you would either increase the pulse repetition rate and or fly lower. Well, I thank you for joining in this afternoon. If you'd like any further information, please contact us at info@riegelusa.com, or you can call us at 407-248-9927. Have a great day.